FreeBSD committer for doc starting from 2008, and for source tree from end of the 2013. I worked for government and ISP and mobile operators, so in various IT-related jobs like programming and system administration, etc. I also do some remote works related to FreeBSD, consulting and system administration. And in my free time, I like to hack ARM boards and to make things work. And last but not least, I like to play football. So in my free time, sometimes I play football. So today's content would be a bit about introduction, what is CIR is, and then later on about A10 and A20 SoC consumer IR, and a bit about CIR driver, Evdev interface, what is it, and then how to use the Evdev interface in CIR driver, and we'll do some tests, how to test CIR driver, whether it works or not, and then I will try to demonstrate CIR driver working in one of ARM boards, and there will be some conclusion about my presentation. There are many input devices like keyboard, mouse, touch screens, and things like that, and infrared is also one of the input devices. So in order to work all these devices in operating system, they have to have corresponding drivers. So basically this presentation describes about writing infrared driver, input driver, in case of a consumer IR controller. So with using a new Evdev interface. So remote control or consumer IR, they call. So all these TVs and DVD players, set-top boxes, or Android TV, dongles or sticks, they mostly have remote controls. So what is CIR is, according to Wikipedia, it refers to a wide variety of devices that uses infrared electromagnetic spectrum for wireless communications. So looks complex, but in a simple way, CIR is used for remote controls to infrared light. So there are lots of ARM boards that have CIR controllers these days, like especially for Chinese all-winner SoCs and some other chips they have. So as I said, most of the all-winner SoCs have CIR, like for example A10, A13, A20, A83, H3, etc. So I think those are the, if I remember correctly, have CIR. And then as for A20 based boards, they expose IR receiver. Boards already have IR receiver, so those can be used. For instance, like Kubi board and Banana Pi, they have A20 SoCs. So as I said before, major players like set-top box and those have built-in standard CIR infrared receiver for 38 kHz based IR controllers. So those can be used, and as for software, there is software called LIRC, it's compatible for most of the data center remotes made for computers, DVD players, etc. And as for 810 and 820 SoC CIR features, it has like full physical layer of implementation. All these are according to the public documentation of A10 and A20 SoC. And it supports CIR for remote control, wireless keyboard thing, and then it has dual 16 by 8 bits FIFO for data buffer, and programmable FIFO thresholds, and also it supports interrupt and DMA. So basically that's from the documentation of the A10 and A20 SoC. Data is messy, but some says like 64 by 8, but in some doc it says 16 by 8. So the CIR driver itself is based on, as I said before, public documentation of A20 SoC, and I found out that Linux and C BSP driver is mostly useful one, because there are also other drivers based on that, but those are kind of messy and hard to understand, and didn't work for me. So basically the BSP driver case worked for me. And as for driver and FreeBSD, in driver's probe function, it detects compatible string in device tree, all winner sum for A10 IR. So that's in device tree DTS file. And initialization in attach function. First, it sets local related initializations, like gets clock from device tree, APP and IR clocks, and then it sets rate for IR clock, then enables these clocks. And later on it enabled CIR mode, and it's bits 4 and 5 in IR control register. And then later on it sets clock samples, filters, and idle thresholds. And continues like inverting the input signal, and some RX related initializations, like clears all RX interrupt status, and then enables RX interrupt in case of the overflow, packet end, and FIFO available. And then later on it enables IR module. So then like the main thing comes, it uses Evdev interface, initializes. And later on there is interrupt handler in case of like RX FIFO data available and packet end. And then of course decoding and validation of raw codes, but this part is kind of also messy, so I just followed the Linux and C BSP driver. Okay, so Evdev interface. So what is Evdev interface is? It's just a generic input event interface. So compatible with the Linux Evdev API at IR control level. And it allows using input event if the drivers in XOR, VLAN, Qt, etc. So basically it generalizes raw input events from device drivers and then makes them available through character devices in dev input event form. So basically that's the main place. And then of course it seems for me very flexible. So like easily representing the multi-touch events, like from touch screens, mouse buttons, IR, and so on. As for Evdev support, it was started by Jakub Klama during the GSOC 2014, and then later on updated and finished by Vladimir Kondratyev. And recently, like a few months ago, Oleksandr, he just committed Evdev-related support, including some hardware drivers like UKVD and UMS. So I would like to thank these guys, and also some ARM people like Manu, Jared, who made all these things very easy for all winner SoC support. And the related source codes are in sys-dev, evdev. So basically, the codes are there, so everyone can look at it, and I think it's self-explainable. So in case of the interface, each device provides one or more dev input event nodes that processor can interact with, and then it includes checking capability bits, like for instance, does this device or have a left mouse button or right mouse button or things like that, and then it can read events from the device. So what are the events? It's a single hardware it generates multiple input events, and then events are in form of structure, input event, and its location is here, input.h. So it has following fields like event type, like it can be relative, absolute, key, etc. They describe this, and then basically it's a group of codes under logical input construct. So then each type has a set of applicable codes to be used in generating events. Then next thing is event code. So like x-axis, left mouse button, or things like that. And this is just defines the precise type of event. And so list of event codes are in this location, input event code.h. And there are also two other things, timestamp and the value. Value is itself the read value. So basically, the events are in form of struct event, input event.
I have a question.
Yeah.
What is the meaning of M? Dev input event M.
This one?
Yeah, that is.
That's just a number in it, like 0, 1, 2, 3, or 4.
No. I am meaning the M, or the target. And I mean the target what? And the number of devices or keyboard, mouse, or something like the input devices that are equivalent to the number of N. For example.
Yeah, I mean, for the devices, I mean, drivers that use Evdev interface, they have a node. I mean, each device has a node. So, for instance, if the first device was using Evdev, then this one would be event 0. So it's not the number of devices, but it's the device node allocated for each node.
Oh,
so
thank you.
So as for event types, there are various event types like I've seen. It's like used for as a marker to separate events. So events can be maybe separated in time or in space, such as with multi-touch protocol. The F key, so it's related to the changes of the keyboard buttons. And then FREL, so used to describe relative access value changes, like moving the mouse 5 units to the left, etc. And then ABS used to describe absolute access value changes, describing the coordinates of touching on touch screens. So these are the event types. So in case of IR, CIR, we will use MSC. So it used to describe miscellaneous input data that doesn't fit to other types. And there are some other event types like SW and FLAG, FSND, FREP, and then FFF, etc. So all these are event types that can be used. So again, in case of events, so all the events are serialized or framed by the events of type fSyn, and then called syn report. So anything before it considered to be one logical handle event, and like for instance, if X, Y movement, then that means like diagonal movement. So event coming from physical hardware goes to first the kernel's input subsystem, and then converted to the Evdev event, and then available on event node. So basically that's it. And then like events and reports can be discovered based on the device capabilities and state. Like for instance, consecutive events with same coordinates. In this case, they will discard all the one except the first one. There is also one thing, U input. This is a kernel device driver that provides dev U input node. So process can interact with it, sending or writing some commands to it. And then kernel creates the virtual input device. So it's in the form of dev input event. So event written to dev U input node will appear in dev input event. So U input device looks much like a physical device to a process. And in case of U input, common application that uses it is like, for instance, FMO tool. So I didn't check this tool, what it does, but I think it's the main consumer of U input. So in case of U input, to set up U input device, it uses same Evdev type and code combinations, but then it uses U input specific I/O controls, and uses same event form struct input event, and there is like third-party tools or libraries like libEvdev that can be used to initialize U input devices. It's kind of easy because it has U input related functions. So this is basic picture describing what is there, U input and devices. So those are the input nodes. For instance, this case for mouse, event 0, and keyboard, event 1, and other like IR or touch screens, maybe like event 2, 3, or something like that. So, and then the event the tools first interact with U input, and then this one creates virtual U input device and represents this event node. So on the user space side, like this libinput, libEvdev, LIRC, etc. So this is just basic picture of Evdev input, U input, and devices. So Vladimir gave me this picture, and this is more detailed data flows with Evdev. So on the hardware driver side, there is Evdev set and Evdev support functions, which sets like descriptions, including name unit, hardware IDs, etc. And then Evdev support sets capabilities, and like Evdev push related functions like capabilities filters, then event modifications, test filter, etc. So on the user side, user is a user-land programmer software. So this on this side, these programs can access directly to the event nodes via syscall. So basically, this is what's inside of Evdev. So to use Evdev in CIR driver, there are only a few lines of code. Like first, it just allocates memory for Evdev, then as I said before, sets the name, and then sets the name unit and set ID, and then it says support evsyn. So evsyn, we will support evsyn here, and then MSC, we will support MSC. Then it will support MSC scan code. Then later on, Evdev register to register this Evdev. So basically, these few lines of codes are needed in device attach function. Of course, there are some kernel options that needs to be added in the configuration file. These are the lines that I added to ARM generic kernel config, like Evdev support, so device Evdev, and then for legacy ones, Evdev support. This line is needed. So, and then U input, I added this for consistency, and then our driver, AWCIR, so these are in kernel config. So these are the minimum in case of CIR driver. So, of course, there might be needed to debug some, in case if driver doesn't work, or I don't know, in case something is not working, there are options Evdev debug and options Evdev U input debug. So these are the for debugging. And later in the codes, of course, when we want to send hardware-generated events, like Evdev push event and Evdev sync. So these are the functions need to be used to send IR codes. So here is the example, like in case of CIR, MSC, and then this type, and then MSC scan code, and then actual IR code itself. So and then we Evdev sync to sync the event. So now we have written the CIR driver, so we have to test it some way. I mean, whether the driver works okay or not. So there are some tools exist already, like Evdev dump. So this is a very simple utility for dumping input event device streams. So again, this was adapted to FreeBSD by Oleksandr. So this is the address where the FreeBSD adapted Evdev dump is there. And there is also one tool exists called Evtest. So compared to Evdev dump, it can list the devices and dump device capability, etc. But it can't dump more than one device at once. So Evdev dump is a simple and good one. So here is the sample output, like we run this Evdev dam on and specify the event node. So when you press some button in the remote control, so these are the things it shows, like this one is event node, and this one is timestamp, and this is event type MSC, and then event code is MSC scan, and the actual code itself, and then fsyn and syn import when it syncs. So these are what it shows in case of CIR driver. There is also one tool exists from multimedia V4L utils. So this is IR key table. So again, it can list remote controller devices and allows to get and set IR key code, scan code tables. It can test events generated by IR and adjust other remote controller options. So we can run like this way, like IR key table, argument T and D to specify event node. The output is a little bit different. I don't know why it says like event type is null and then some code. So basically, for testing, I think it's okay. Like at least it shows some timestamp and scan code itself. So, which means something is working. So in case of demonstration, I used 2 devices at home. Like one is QB 2, and I also tested it Banana Pi M1. But during the test, somehow I broke my Banana Pi, so I brought the QB 2. And then I used a simple remote control. This one is from DF Robot. I bought it to use it with Arduino, but I didn't use so. But in this case, I used so. But there are also like other remote controls can be used. And then there's software-wise, I mean in user-line software, I use LIRC. So there are 2 tools used with the LIRC. One is IR record to record the keys, and then IR exec. So I use all this for demonstration. Later on, using IR exec, I will show you how to turn and off, on and off some LEDs on a device. So what I did is first I had to fetch some NEC related remote config files from this location because this file has some protocol descriptions, etc. And then I had to record the keys using IR record. So this command was used to record the keys. So just to test, I recorded like 2, 3 or 4 keys. And then after I finish this program, it will be stored in this form, kind of ugly, but that way. I don't know why it works that way, but it worked this way. And then later on you can check, not later on, you can check also what key names are allowed. So with the command IR record L.
Excuse me.
Yeah.
So this is some kind of what do you call that? Learning mode. This is for IR learning.
Yeah, some kind of learning mode.
Okay, so some kind of stuff that you do, you used to do with universal IR remote?
Yeah, I mean like, there are some, I think, key names allowed with LIRC. And those can be listed this way. So first you will see what other key names are allowed. then you have to use that key names to learn things with the IR record. So first it asks the name, key name. So you type like key _1, and then it asks press that key. So you press it, and then like that it follows. So
Okay.
so, yeah, kind of learning one. So after you learn the IR record, so like it becomes like this one in a config file. So begin codes, end codes. So inside key 0 or key 1, I press like 2 in case. So like this form. So probably, most probably this one is important. So all the zeros are not needed. So we will delete these zeros. So it becomes like this one in config. So later we have to copy this config to the real location. So real location is here, USR local etc lrscd.conf. So, and then of course it needs those lines in order to start LRC. At boot time, we will need to specify what event node we are going to use. So after starting LRC, we can check by this command, using this command, whether it works or not. So like output would be like this, like key 0, my remote is in a config file. I just rename it inside the name. So something like it will show So I'll show something on the board. Let's see. First the Evdev dump. Let's see. So see, can you see? Let's see, bigger. So if you press something there, something there, something there. So this way it's possible to test. And there is this one IR key table. So similar, but with this one. So something is working, right? And let's see, IRV, yes. This one is there, this, right? So pretty handy, all these tools to test the driver. Now, let's see. So we see that the CIR driver is working somehow. Now for the real test, we will use IR exec. IR exec is pretty handy. Like it defines the key and what we are going to use, IR exec, and it basically executes the command here, written here. So this one is like turning on the user green LED, and key one is like turning off, and this one is turning on user green LED, and this one is like key 2 turning off the blue user LED, and then key 3 is turning on the blue user LED. So these are the IR exec config files, so we have to put that in USR local etc lirc and lirc rc. So this is the location. So we will put this into that location file. So back to the test. We have to run IR exec. So this one is running. So let's see. Can it turn on off something? green, blue. Blue is kind of small, right? So we can turn off, let's see blue, yes. You can see both. So it works, and then I have other remote controls, so we can use that one. I created some script, just copies the right files in the right place, and then so it should work, I mean. Yes. So, working? So I think any remote control can be used. So back to presentation. So basically, that's it. I mean, using Evdev interface in driver is easy and straightforward. And like, there are some sample drivers already exist. You can take a look at the codes like UKBP, UMS, and like TI ADC touchscreen drivers, and like including this one, CIR driver. And then testing was easy, like using Evdev dump and IR key table. You can see whether the driver is working or not. And of course, like the IR is very handy. Using IR, I mean usage of IR is very broad. So like in our case, we use LIRC to control GPIO, LEDs, and I mean GPIO. I didn't test GPIO, but I mean it goes via so LED, and then IR record and IR exec is very handy tools. And FreeBSD all-weather CIR driver. So in case of that, it can be based on data SOC CIR drive controllers, and may need some small changes in order to make it work for other all-weather SOCs like H3 or something like other things. And yeah, basically that's it. So it was easy enough to write the driver using Evdev. So thank you for your attention, and if you have any questions, please.
So can you use any remote? Or are there some brand of remotes that will not work, or because of the physical protocol is not the same? I don't know much about this stuff, so.
Yeah, I mean, I think it's possible to use any remote control, but I have only tested two, so there might be some other like already made configurations with protocol descriptions, like NEC.conf, maybe like Sony.conf. Things like that. So maybe have to try and see how it works. So.
Okay.
Yeah. Okay, any other questions? Okay. Thank you for your attention.